Okay, last new thing. Complex numbers. Do you guys remember? I'll give you that. Do you guys remember anything about complex numbers from Algebra 2? No. No? Kind of? Okay, so most of you guys remember this thing. That when this happens, you make this new symbol I. Right? And okay, so I should clear one thing. Imaginary is the dumbest label for this ever. You use these all the time. Every time you drive your car down the road, you use an imaginary number. So don't tell me they're imaginary because they're there. Okay? So it's just a really poor label. They come up all the time. You can't do electrical engineering without them. You can't do anything that oscillates or bounces without them. Those sine and cosine function are really kind of inherently in here. And we're going to see why. Okay? Okay. I need this, and then I claim you guys know everything else you need to know. So let me give you an example of a complex number. How about 2 plus 3i? It's okay. It's not that complicated. So say I wanted to graph this thing. Right? This is like a number. I should be able to draw it on a number line, right? Okay, I can't draw it on a number line, but I can draw it in two-dimensional space where I do real numbers this way and imaginary numbers vertically. Okay, now how do you suppose you graph the number 2 plus 3i? Yeah, you go right 2 and up 3. See that? This is the real part. The part without the i's is the like x coordinate. And the part with the i's is like the y coordinate. You guys see that? So this is the number 2 plus 3i here. And if you really want to, you could really think about that as the point 2 comma 3. You guys see that? This is why I claim you already know everything you need to know about the complex numbers, except for how to convert. You see that? I promise these are actually interesting, because this is the only reasonable example of a space where it makes sense to multiply vectors. So another thing you could think of here is the vector 2 comma 3, right? You guys see that? Remember we had that interchange between kind of points where we were thinking of just a dot, right? And vectors where we were thinking about a vector ending at that dot, starting at the origin. You guys remember that? Okay. Let me give you an example of multiplying vectors. So let's multiply 2 plus 3i times, I don't know, 1 plus I. Say that louder. FOIL. Right? Okay, so if you FOIL, what do you get? You get 2 plus 3i plus 2i 3i squared. What's 3i squared?
Negative 3.
Negative 3, right? So this is 2 plus negative 3 plus 3i plus 2i, which is negative 1 plus 5i. So I took the vector 2 plus 3i and the vector 1 plus I. Oops, that should be there. And somehow I multiplied those and I got the vector that's back 1, up 5. You guys see that?
Where'd you get the -3 from?
So the only thing that makes complex arithmetic different than regular arithmetic is that when you square I, you get -1 out. So all you do is you FOIL, and then when you get I squareds, you replace them with -1.
Oh, so you just multiply it. Okay.
So the square root of -1 times square root of
Perfect, because it's the square root of -1 times the square root of -1. So it's the square root of -1 squared. So hence the -1. You guys cool with this? Okay, you want to see why we're talking about this in trig class? Okay, so right now this process, right, take this, take that, get this, did not make any damn sense. You guys see that? You want to have that make a little bit of sense?
Yeah.
Okay, what happened there, and we'll see this in a second, is that I took how long this vector was and how long that vector was, and I multiplied those together. That tells me how long this vector is. And then I added the angles together. You guys kind of see that? That would be much easier if I learned to think about these in polar, right? Okay, so our goal is going to be to develop the polar form for complex numbers, because then we can play trig tricks instead of playing algebra 1 tricks or algebra 2 tricks. Cool? All right.